all the ethers. There was a couple we did not do, left it for you to do. Let's see. By the way, why is tosylate a good leaving group? You don't have to propagate it. I don't know if we pointed that out, but the oxygen is very resonance stabilized when it leaves. Look at the oxygen anion that leaves, you can draw resonance into the sulfone. Okay? This was pointed out. When the nucleophile kicks off the oxygen, we end up with the nucleophile on that carbon plus the leaving group, the oxygen. There's your leaving group, but you got resonance. You can draw resonance structures. So please make sure you just recognize that, able to draw resonance structures there. The tosylate is a great leaving group, resonance stabilized leaving group. I think one at the bottom, couple at the bottom. Did we do the first one in class? We didn't do either one of these? No? Tosyl chloride, pyridine, what does that do to an OH? Something for a note card. Converts the OH, put the tosyl group on, yeah?
Yeah.
Okay, we've already seen the mechanism. So that's 1 is just going to give us O. And now we have the tosyl. I'll draw it out. Or at least partially. That's generic for the aromatic ring there. We have the tosylate. Or this might be shown as O-tos. Yeah? Okay, we've already looked at that. That's the first step. This can be isolated. When we make the tosylate, is there any change here?
Yes.
No, when you make the tosylate, nothing happens over here. The oxygen attacks the sulfur. Do your mechanism. Now the oxygen is bonded to the sulfur. No chemistry takes place here. There's no change in stereochemistry there when you make the tosylate. Get back to the mechanism. Nothing happens over there. There's no backside attack. There's no chemistry there. That's the same. Still bold. As long as the backbone's the same. Sodium azide. That's a good nucleophile. That's Na plus, N3 minus. That is ionic. By the way, cesium fluoride on that little mechanism is ionic. Y'all take Gen Chem? Ionic versus covalent? Cesium fluoride is not covalent. Now we're all trying to make covalent bonds between cesium and fluorine. It's not covalent. This is not covalent. That's just Na plus N3 minus. I mean, if I show you NaCl, that's 2 ions. I mean, that's just really just formula there. It's 2 ions. This is N3 minus. N3 minus, though, was introduced in Organic 1. Here you can show a full Lewis structure. You really got 2 minuses and 1 plus for a net minus. To put a lone pair there, you really need a full Lewis structure. But in the end, there is a lone pair there. Now we can do a nucleophile and kick that off. SN2, yeah? What does that give? The N3 is now bonded to this carbon in place of the leaving group. We're going to get inversion of this carbon. And so we can draw the product. If I just want to replace the leaving group with the N3, then I can draw the deuterium like this. That is indeed inversion. Hopefully you know all the details and nuances of inversion. Okay? That look pretty straightforward. Make the tosylate to make the OH a better leaving group, and then you just do an SN2 with azide. Questions, Vernon?
What's the chloride in the tosyl alcohol?
Why is the chloride?
Why is it not involved in what is it not? Yeah.
Which step? First step or second step?
Second.
second step, there's no chlorine, it's just this.
So it doesn't come up from the top and then attack anything?
Well, this mechanism was done up above. Do you have the mechanism drawn above? We've already done that mechanism. All you got now is tosylate. This is isolated, purified, it's a pure compound. You throw in a nucleophile, backside attack, boom. Let's do the next one. We have aromatic ring and alkyne inbutyl lithium. What chemistry is happening in step 1? We have this acidic proton here. The H of a terminal alkyne is acidic. Inbutyl lithium is the great base. Can be shown ionic. Inbutyl anion, lithium plus. Hopefully everybody saw inbutyl lithium in organic 1. First step is this acts as a base, takes the H, leaves a lone pair behind, and we get the phenyl. Anion here minus plus butane. It's just an acid-base reaction. Now remember the chemistry of terminal acetylenes. The H can be removed. Inbutyl lithium is a common base for that. NaNH2 is a common base for that. Now we're throwing in dimethyl sulfate. Dimethyl sulfate, right there. I'm not going to redraw it. These electrons, that's a good nucleophile. It's a good electrophile. The carbon has a leaving group. Attack that carbon, kick off that oxygen. That looks a lot like an O-tosyl. And what do we get? That carbon is now bonded to a methyl, supplied by dimethyl sulfate. Just a good old SN2, yeah? So here we made the leaving group of the main substrate. We made it a better leaving group. Then we came in with a nucleophile. Here, the base made this a nucleophile, and then we threw in this electrophile. Questions about these two examples? Largely review from Organic 1, standard chemistry. A couple of activation steps. Next page, alcohol. I think we did the top one, yeah? This one was it bold with a C in? What's this product going to be? Going to be dashed. What does hydrochloride pyridine do to this? Converts it to the tosylate. Can I just do that? Now you got the top. Did we do any chemistry here when we make the tosylate? No. Now we bring in the CN minus. Backside attack, kick it off, SN2. You only have one inversion. Up here we had two inversions. Because when you react the alcohol with PBr3, you're replacing the oxygen with the Br. The Br comes in backside there if you look back at the mechanism. And so getting your leaving group there did an inversion. But here, getting your leaving group there did not do an inversion. Because the oxygen didn't leave. The oxygen just bound to something over here. Top reaction has two inversions, and thus you get back to bold. This one only has one inversion. That make sense? About the one at the bottom. is alcohol with HF. What mechanism are we doing here? Somebody said E1? How do you know we're doing E1? Please don't tell me because we're under Roman numeral 2, dehydration, and then it says E1. You got to be able to look at a reaction out of context. Like on a final exam, when there's 5 reactions and there's all types of possibilities, and say, okay, what mechanism am I doing here? Indeed, it's going to be E1. Why not E2? There's no strong base. Why not SN2? Why not substitution here? Because substitution requires a nucleophile, right? Has anybody ever considered that substitution requires a nucleophile? Guess what it does? Is there a nucleophile here? F minus? F minus is potentially a nucleophile, but I've said several times in Organic 1 to my guys, F minus is never a nucleophile with me in Organic 1 and 2. It's a lousy nucleophile. Okay? There's no nucleophile here. All you got is acid. So is it SN1? I don't know how, because there's no nucleophile. The only thing it can be here is E1. Okay? You got to be able to rationalize your thoughts. Now that it's E1, mechanism is going to be what? Protonate this. Then it ionizes. What's the product? What product does E1 always give? Always get Zaitsev product. That alkene. Questions? Again, I'm not going to take the time to go through full mechanism. You should know the mechanism. Or you should sit down and work it and then ask questions about it. Our class time is very limited. I'm trying to take you through the rationale, my thought process, or what I hope is your thought process. Okay. Another one on the flip side. What mechanism do you want to do there? Do you have a nucleophile? No, you got acid and you got phosphate. Phosphate will never be a nucleophile for us. Sulfate will never be a nucleophile. There's no nucleophile, so guess what? You're not doing substitution. How about E2? No, there's no strong base. What's the mechanism? E1. E1 gives an alkene. Which alkene? Most stable. What's the product here? Somebody already got it on the paper, hopefully? Phenyl. Let me draw the ring out. Dehydrate this alcohol to this here by an E1 mechanism. Why that and not that?
Conjugation.
Very good. They're both disubstituted alkenes, but can you make an argument for which one's more stable? This one, double bond conjugated with the ring, will be more stable. E1 always gets the most stable product. And of course I drew a trans, because trans is more stable than cis. E1 is easy to predict, always the most stable alkene, because E1 is ultimately an equilibrium reaction. And the most stable product is going to win out in your equilibrium. Not so with E2. Questions? Aquapiridine. Aquapiridine is a way to dehydrate alcohols by an E2 mechanism. It'll be better for primary alcohols because trying to dehydrate them by an E1 very difficult because you don't want to make a primary carbocation. Not only do you not want to, but that molecule doesn't want to. Did we do this mechanism? I think I maybe showed you the pockle. Pocklepyridine. Here's pockle, first step, these electrons attack the phosphorus, what you want to do?
Kick off the bond.
Pi bond breaks, weakest bond breaks. Breaks away from the phosphorus, that gives the H is there, the oxygen is now bound to the phosphorus. This oxygen is now minus, so now it has 3 lone pairs. Chlorine, chlorine, chlorine. 1 lone pair here plus charge. Net neutral, net neutral. What you want to do now with this guy? We just did an addition. Anytime you can make a pi bond, you kick off a leaving group, that's easy to do. Somebody keep track. We'll say that about 100 gazillion times this semester. Let's make this pi bond and kick off a leaving group. Which one do you want to kick off? You might say, which is a better leaving group, protonated oxygen or chlorine? Which one do we need to kick off? We need to kick off the chlorine. Hold on, before we kick it off, let's take care of the proton. Very often we're going to have to take care of what looks like an acidic proton. We got some base in there, pyridine. These electrons take this H, which looks acidic, like H3O+, leave the electrons behind, and we get oxygen, P, 3 chlorines, now that's minus. We're going to make a protonated pyridine also. Now let's remake pi bond. When these electrons come in now, which is a better leaving group? Plain oxygen or plain chlorine? Plain chlorine. Now we don't have to wonder which. Now we can kick that off. Make pi bond kick off leaving group. What does that give? Phosphorus double bond reform, 2 chlorines on there. Everything is neutral. This is almost like a tosylate now. The tosylate would have SO2 and an aromatic ring. But this is a good leaving group. Now, what are we trying to do ultimately? We're trying to put a double bond in here. Why do I have 5 carbons over there? 1, 2, 3, 4, 5. 1, 2, 3. I'm missing a carbon somewhere. Why didn't anybody yell? 1, 2, 3, 4. 1 more carbon there, yeah? Yeah, is that right? Pyridine is strong enough to do an E2. At this point, these electrons take one of these H's. These electrons can move in. And this is a good leaving group, like a tosyl. And what are we doing right here? A concerted E2 elimination. And that's going to give here. Basically, we activate our leaving group with the pockle, and then we do the elimination. How many equivalents of pyridine did we use here? We actually used 2. It doesn't stay there, but you're actually going to use 2 equivalents of pyridine. This looks like a good old E2. Yeah? Pyridine is strong enough to do an E2. Did we make a carbocation here anywhere? No. We're not doing E1. That would have had to be a carbocation because there's no strong base to do E2 in sulfuric acid. Okay. You can do this one on your own. Careful down here. What's the stereochemical requirement of an E2 elimination? Do you always get the most stable alkene? No, you don't. Because there's a stereochemical requirement. The leaving group and the beta hydrogen that's abstracted have to be what during the transition state? Anti-coplanar? Well, it has to be coplanar. Anti is highly preferred. It can be syn coplanar. But anti-coplanar is highly preferred. Keep that in mind down here. Okay. Let's start fresh here. Oh, alkylation. What's it, the green sheet? We've done substitution of alcohol. We just did elimination where you essentially remove water. Next, we're going to do O-alkylation. We're going to put an alkyl group on the oxygen. The oxygen is still going to be in the molecule. Up there, we replace the oxygen. Here, we eliminate the oxygen. Here, it's going to still be in the molecule. We're just going to put an R group on it. Alkylation. And what functional group are we going to get if we put an R group on the oxygen? Ether. And the most common, well, there's really only one way to do this, and it's called a Williamson ether synthesis. Just about any reaction that has a person's name associated with it is going to be a highly important reaction. Typically going to be an SN2 reaction. It doesn't have to be, but the majority of examples are. Is a neutral alcohol a good nucleophile for SN2? What type of nucleophile is needed for SN2? Strong. Needs to be strong because it's a bimolecular mechanism. How do you determine a strong nucleophile? My guys, what do we say in organic 1? Either an anion or an sp3 nitrogen. Is that an anion? No. Is it an sp3 nitrogen? No. It's thus not a strong nucleophile and cannot do SN2. What if we can make it the O minus? Everybody sees the O minus there, right? That's O minus Na plus. We can make it O minus, it will then be a good nucleophile, and then you can do chemistry. We got to deprotonate this, remove the proton. One of the most common ways to do it is just to react it with sodium metal. We cover this in organic 1. This is actually not an acid-base reaction, but it's actually redox. Reacting alcohol with sodium metal, you'll get the sodium alkoxide. It's spelled with a K. I means anion. Oxide. I mean, that's kind of like oxide, but it's got an alkyl group on it. RO minus. This is your R group. O minus, sodium plus. React with sodium, you get that plus hydrogen. There's only one H here, there's 2 there. If you want to balance it, do that if you want, but it's not balanced. Okay? It's a redox reaction. Here the sodium is sodium 0, sodium metal. Here it's sodium plus, so the sodium has been oxidized. Actually, the hydrogen's been reduced because here you call it +1. Here, elemental hydrogen is 0. So we're not going to show arrows because redox reactions are hard to show arrows. They're usually radical reactions. Very common. Did we demonstrate putting sodium in alcohol? I think to half of my guys in organic 1. Did we do that? And it started bubbling, generating hydrogen. Very common way. You can also make the alkoxide with sodium hydride. This is actually sodium plus H minus, yeah? That's where H has two lone pairs and a minus. Hydride is possible if you haven't seen it before. There you can show an acid-base reaction, because it truly is. Draw a covalent bond, these electrons bond to the H, these electrons move on to oxygen. The oxygen now has three lone pairs and it's a minus. And you also generate hydrogen. But this is a standard acid-base reaction where you can show a mechanism here. So the first step is to convert the alcohol to a good nucleophile by removing the H. So here's a typical line reaction. What does sodium do to an alcohol? Converts it to minus. Can I just do that or something? Okay. Refer to the previous page. Now we throw in this guy. What type of chemistry do we predict? We got a good nucleophile. We got a carbon with a leaving group. Also benzylic. These electrons attack the carbon, kick off the chlorine. Good old SN2 reaction. What's the product? Oxygen is now bound to a CH2. And that CH2 is bound to benzene ring. Under my hand used to be chlorine, but now under my hand is the nucleophile. What bond did we just make? I like to highlight the bonds we just made. We just made that O-carbon bond, right? By a good old SN2. We made an ether. This is called a Williamson ether synthesis from an alcohol. Deprotonate and then do an SN2. This is an alkyl group. I mean, that is, and then the alkyl has the aromatic ring. But we put an alkyl on the oxygen, we alkylated the alcohol. Questions about this two-step Williamson ether synthesis?
Is there somebody stereochemistry on the edge?
You mean on this carbon?
Yeah, on the carbon.
Yeah. Did we do any chemistry on that carbon? No, we didn't do anything there. There's no change at all there. It's the same exact as it was over here. We didn't do backside attack here. We did backside attack there, but there was no stereochemistry there. Phenols. Phenols are more acidic than alcohols. pKa about 8 to 10. Regular alcohol is about 16. So these are like a million times more acidic. Because they're more acidic, you don't have to use like sodium or sodium hydride. You can use a very common base, sodium hydroxide. Spectator ion. Let's get rid of them. By the way, that cesium in the mechanism was a spectator ion. This is sodium plus hydroxide minus, right? Y'all learned about spectator ions in Gym Chem? Hydroxide takes the H, these electrons stay behind. Make the O minus plus what? Plus water. Now remember the acid base here. What's the pK of water? 16. Which side's favored? 10 or 16? 16 is favored. The side's favored by how much? 10 to the 6. A million. This would be your, not an alkoxide, but a phenoxide. It's the anion of a phenol. But it's a good nucleophile, even though it's resonance stabilized. We don't show it. Well, I showed it over there like that. What's centered with this O minus? sodium plus, right? I mean, the spectator ions there just show, you guys seem to think that that's covalent. But when something's shown like that, it's just kind of shown as formula, and there's really charges there. Again, it's like me showing NaCl. Except here it's Na this. Okay, down below, there's an example lime reaction. Take 30 seconds to see if you can show the product there. What's the KOH do? Deprotonates the phenol, right? What else could it do? Remember, if you're considering a million things on a final exam, you got to think broadly. The only thing hydroxide can do to this molecule is remove the H. And at the end of this course, that will still be the answer. No other chemistry. Okay, we've already done mechanism. Hydroxide takes the H. Can I just remove this and show minus? Now we got a good nucleophile. Even though it's resonance stabilized, it's still a good nucleophile. What do we have here? I got a tetrahedral carbon with a leaving group. That's a good leaving group, right? Can I substitute it off by an SN2? Yes, that's what tosylate's for. You don't have to protonate it. These electrons attack there and kick that off. That's attacking the backside. Actually, backside, that's in the plane here. Don't mess up on the paper, but since that's that way, it's actually right in the plane. Backside is right there. Boom. But in my product, I'm just going to draw it over here. Doesn't matter how you draw it, as long as you get the stereochemistry right. The nucleophile. This option is now bound to that carbon. So there's the carbon. What's on that carbon? A D. I'm going to draw it like that. We're going to have to put some stereochemistry here. What else is on that carbon? Ethyl. What stereochemistry do we expect? Now the way I would do this is basically, what do we have here in terms of stereochemistry? Oxygen is 1, carbon's 2, deuterium is 3. What's going back here? That's 4. So it's 1, 2, 3. Counterclockwise, what is this? S. That should be R, unless 99% of the time it's R, and I don't think you should ever worry about 100%. So to make this R, how do we want the D? Well, that's going to be 1, that's going to be 2, the D is 3. For this to be R, do we want this bond to D to be bold or dash? Bold, yes. 1, 2, 3, R. H is in the back. D got inversion. But somebody's wondering, well, why is that bold and this bold? Shouldn't we have inversion? Well, that's because I drew the backbone differently. It is inversion. That's S, that's R. Don't fall in the trap of this is bold, that's good. If you want to draw this dash, you're welcome to it. I could also draw that dash and it'd be the same exact molecule. Just like I can show you my hand with the thumb forward, or I can show it with it back. It's the same hand. Don't fall in the trap of bold has to go to dash. I recommend you check your R and S. Does that look like a William and ether synthesis? What bond did we just make? Is that right there? That oxygen bonded to that carbon? In place of the tosylate? Okay. This class will introduce and use multi-step synthesis. Here's our first look at it. Given a product, can you show a reaction that would give that? And eventually we'll do multiple reactions. Provide a Williamson ether synthesis of the following compound. By the way, that's methyl tert-butyl ether. What are the two components of a Williamson ether synthesis? More specific, not the base. Everybody agree you need to have the O minus. That was one component. What's the other component? It was in the examples. What? Carbon with a leaving group. And since you're doing SN2, that carbon better be tetrahedral sp3. Yeah. You need a carbon with a leaving group. Maybe I can show it like that, where the X is the leaving group. Hold on, let me change that to LG. Make it more clear for you. Everybody agree what we just did was this here, and we put another R group on the oxygen? That's what the Williamson ether synthesis is. We need the alkox side and a carbon with the leaving group. So when we want to go backwards, and this means a double-headed arrow means we're going backwards. It's called retrosynthesis. I showed you what bond we made with the little line. What bond would you like to break when making the Williamson ether synthesis? You want to break that carbon-carbon bond? No. You make an O carbon bond going forward, so going backwards you want to break the O carbon bond. We can break here, I'm going to call that A. If we did, we would get what? That minus, and what? What's your favorite leaving group, so? Iodide?
Sure.
I can't hear you. Put a leaving group on there. And then we could say, coming forward, oxygen could bond to carbon, kick off the iodide. You're shaking your head no.
No,
Good. Why?
because you want the leading group to be on,
That's a tertiary
yeah,
carbon.
tertiary, you want to be on primary.
Do you do SN2s on tertiary carbon? No. Theoretically, this is a good separation, but then if you think mechanistically, this is no good. Because you would never say this is going to attack here and do an SN2. So instead of making that oxygen-carbon bond, can we make another oxygen-carbon bond? How about over here? That's the A way. We go backwards to B way. What is this, a methyl? That would be just a CH3. But it would have a leaving group that the oxygen is going to replace. Let's put an iodide there. And then over here we would have that minus. Would this work coming forward? I had this O minus. Will it be attacking this here and kick off the leaving group? Put a methyl? Sure. That's a nice SN2. Primary carbon with a leaving group. When you're proposing a Williamson ether synthesis, you've got to make sure there's two different ways. You can make oxygen bond over here or over here. But then you have to say, is the mechanism that would have to occur maybe here possible? Here's one for you to work on your own. and we'll look at it next time. Including the one below, and then the thing about the thiol is just an example. Any of this chemistry we did with oxygen, you can also do with the analogous SH compounds. What's below oxygen in the periodic table? Sulfur. Very similar chemistry. You can deprotonate that, make it S-. And here, this would be called a thioether, or a sulfide. Okay, let's introduce reactions of ethers. When we do reactions of ethers, it's pretty much just the opposite of synthesis. We're going to break the ether apart into the corresponding alcohol and usually like alkyl halide. First off, ethers are fairly unreactive class of molecules. A lot of ethers are used as solvents because they are fairly unreactive. And really, they only react under acidic conditions. Under basic conditions, ethers typically inert. Under acidic conditions, the main reaction is with HX, these three. And the halide will act as a nucleophile. Because of that, we don't include HF, because F is a bad nucleophile. Now this chemistry should almost be very predictable based on what we've talked about thus far. But the main reaction is cleavage, or dealkylation. We're going to break this molecule apart. Let's just approach it mechanistically and just let it go how we'd like. Let's just go mechanistically, okay? Ultimately, the oxygen is going to leave one of these carbons. What do you want to do first here with HBr? How do you make oxygen a better leaving group? Protonate it. We protonate alcohols. You can also protonate ethers the exact same way. Just show this ionic. Can be covalent, but let's show it ionic. These electrons here. Just protonate the ether. Okay? Let's think mechanistically to help us predict the chemistry. We do have a Br- there. What can you do next? This is a good leaving group. What could the Br- do? Could it attack this carbon and kick off the oxygen? Sure. Let's do that. Let's show two different products. This attack here, that's a methyl it's attacking. See, it almost looks like it's naked. Let's draw in a methyl. And that's what it is there. Give us something to... This attacks the carbon in the methyl, kicks off the oxygen. Is that very reasonable? That's just a good old SN2. What does that give us? That gives us the leaving group plus what? Plus methyl bromides. And now the ether has been cleaved. And we're going kind of backwards. We get back to the alcohol and the alkyl halide. Remember, and if we just remove the H from the alcohol, we got this plus the alkyl halide. We're going back. It's kind of the reverse of synthesis when you cleave an ether. What mechanism is this? SN2. Instead of the oxygen on the methyl, what's now on the methyl? Bromine. The bromine substituted for the oxygen. So that's the SN2 product. What other mechanism could be done here instead of SN2? I'm going to call this A, and A. What else could happen here? What else could, another mechanism could be this oxygen could just leave this carbon. Do you want to show the bromine attacking this carbon and kicking the leaving group off? No, that's tertiary. You would never do that. But what could we do here instead? Somebody said it, ionize. This is alternative pathway. If we ionize, what would we get? That cation plus what? Plus methanol. That was the Lg. Over here, which was the Lg? Actually, in both cases, the alcohol is your leaving group. What could attack this plus? Or minus attacks this plus. Bam! What do you get? You get this, these two products. Still an alcohol, an alkyl halide, but it's different from this alkyl, those over there, right? That was an SN2. What mechanism did we do here? Very good, SN1. Two ways to cleave an ether illustrated here. Which one is going to happen? It can be hard to predict. But in this class, we're going to give some fine detail guidelines. Here's how you do. Here's what I want you to do in this class. When you have a tertiary reaction site present, always go SN1. If there's no tertiary site available, do what? SN2. Did we have a tertiary site available? Yeah, right there. So in this particular reaction, which is favored, the SN1 products or SN2? SN1. There's your products based on what I said we want to do in this class. Because if you can get a tertiary carbocation form, that's going to be quick and easy. All right, we'll pick up here. Please read ahead. Please start looking at the epoxide handout. Please do any problems remaining on this page. We didn't ask about any lab questions. Some of you have lab on Wednesday. Go ahead and head out, guys. If you have lab questions, please ask.